Howdy! Here in Australia we're talking a lot about bringing in a carbon tax and how it relates to climate change. Some guy said not so long ago it must be more than just CO2 that affects global warming. How true that is. But global warming is just one part of the Earth's cycle, which includes global dimming, global cooling and global freezing. How and why do all these different phases of the Earth's climate get going? And what's so special about CO2? Well, CO2 has friends. What do you mean CO2 has friends, you might ask? Well, if you want to understand this, you've got to understand the volcanoes. It's the volcanoes that created our atmosphere, and it's the volcanoes that contribute and continue to regulate it, with, of course, the biosphere. Once you understand the volcanoes, you'll get an idea about what the planet normally does over time. The idea of it being only CO2 just does not fit with the history of the Earth. So let's look at the volcanoes. This won't take a long time, so hang around for 20 minutes or so. This is a list of all the gases and nanoparticles which can be ejected by a volcano when it erupts. You can see that CO2 is just one gas in the gas list. Also notice all the different types of particles in the list on the right. The geological record shows us that when gases and nanoparticles such as these build up in the atmosphere, they contribute to dramatic changes in the Earth's temperature, just as dramatic as what is happening today. In the following schematic, I've attempted to simplify the likely outputs of a volcanic eruption. With tremendous force and often accompanied by base surge deposits, the gases and the vapour, together with large to very fine particles, spread into the atmosphere. Large particles followed by finer particles smother the surrounding area. Finer materials travel vast distances from the volcanic centre. Ultrafine particles, nanoparticles, migrate into the upper atmosphere and beyond, floating aimlessly. The history of the Earth shows us that previous episodes of volcanic activity corresponded with previous episodes of global warming. These volcanic episodes seem to come in large, ever-increasing groundswells which may last for tens of thousands of years before subsiding, and may be due to all sorts of factors outside our control, such as the activity of the Sun, alignment of the planets, or other events even further out in space. Here are a couple of ice core graphs from the Vostok and Epica research programs in Antarctica. The present time is on the left, and the vertical axis is a proxy for temperature variation. Here is the Vostok in more detail over 400,000 years or so. Present time is on the far left. All the graphs show the same general pattern of a fairly rapid build-up in temperature, the red line, carbon dioxide, the blue line, and methane, the green line, and then a slow decrease in all these factors. You can see the major peaks tend to happen in waves or cycles over time, about every 80,000 to 100,000 years or so. Notice that decreasing temperature moves us into the ice ages, and increasing temperature gets us out of the ice ages and into global warming. I have plotted the known occurrences of significant volcanic eruptions on these graphs, and you can see these also correlate with peaks in temperature, CO2 and methane, which are all emitted by volcanoes. Also notice the role of dust in this process, shown as the red line at the bottom of the ice core graph. You can see the settlement of dust as shown by its accumulation at ground level, sometime after the peaks in volcanic activity. The dust's increasing settlement corresponds with the end of the coolest episode or the end of each glacial period. Why does the dust finally settle during the cold periods? Thermodynamics tells us that as the air temperature goes up, so does the amount of moisture held in the air, and so does the viscosity. This creates the ideal sticking conditions for particles to be held in the atmosphere by water vapour and other gases. The particles float in the atmosphere. Decreasing temperatures then lead to drier, less sticky conditions and the fallout of dust. In other words, gases are more viscous at higher temperatures, and therefore nanoparticles settle out more quickly at lower temperatures. Lower temperatures mark the waning stages of volcanic activity, and then the clearing of the atmosphere and the beginning of the sun's rays being able to get through the thinning atmosphere to start the process of warming again. Nanoparticles are so fine they can't be detected by the human eye. You need an electron microscope to see them. They can be made of anything at all. Some are only slightly larger than a few molecules of gas. The finer they are, the more they behave like a molecule in terms of the sun's radiation, and the longer they are able to float around in the upper atmosphere. Whether the nanoparticles are emitted from man's activities or from natural events including previous volcanic cycles, if they take years to settle back onto the Earth's surface, then they will affect the Earth's temperature and also climate. What do these gases and nanoparticles look like? Here I've shown some CO2, sulfur dioxide, water and methane molecules. They are about 0.3 to 0.4 nanometers in diameter. Below this are some airborne nanoparticles of silicates and oxides which have been caught on a filter. They are the tiny white specks which are fractions of a micron in size. Initially, the accumulating nanoparticles in the atmosphere may assist in the heating process, global warming, in a similar fashion to the so-called greenhouse effect. Geological history tells us, however, that as the gases and nanoparticles build up in the atmosphere and form a much denser layer, it becomes much harder for the sun's rays to get through them. So eventually the Earth goes into a dimming period in which temperatures start to go down and we enter a cooling and finally a freezing stage. The good news is that man has survived the last major ice age and lived through many dimming periods. Obviously the degree of intensity is the critical factor. If you look at the timing of these interruptions to our pleasant living conditions, either in the form of volcanic explosions or subsequent dimming and cooling phases, you can see that they had a direct influence on man's actions at the time. The largest, most recent basaltic eruption was the Laki volcano in Iceland in 1783. This caused an extremely cold and harsh summer from Iceland to Siberia. It was very dry and hot in Western Europe, and the 1783-84 winter was extremely severe. There were over 10,000 deaths in Iceland, 20,000 deaths in England, and 16,000 deaths in France. The crop failures every year from 1783 to 1788 were thought to be the major contributing factors in the start of the French Revolution. The impact of volcanoes can be far more deadly than anything man has experienced yet. Throughout the last 500 million years or so, present time is on the right, larger volcanic events can be correlated with mass extinctions of whatever species was around at the time, long before man got here. For example, the relatively recent, in geological terms, outpourings of the Deccan Trap basalts in India, approximately 65 million years ago, is thought by some to have lasted for up to 200,000 years, causing enormous devastation to life on the planet. The volcanic activity in the last 10,000 years can be expressed as those erupting now, perhaps 20, each year 50 to 70, each decade about 160, and during the Holocene, the last 10,000 years, possibly 1,300 to 1,500 volcanoes were erupting. Putting these extinction events in geological context, here is the Holocene on the time-life spiral, and here is man. So the Earth has always been the subject to volcanoes and whatever they would throw out. From a geological perspective, man has only been here for such a very tiny length of time in the history of the Earth. Whether we like it or not, man, just like all the life that happened before, is and will continue to be at the mercy of the volcanoes. The ice cores showed that about 16,000 years ago, the Earth had large concentrations of dust settled at ground level and low concentrations of CO2 and methane, indicating low volcanic activity. It was the end of a cooling phase. This corresponded with our emergence out of the last ice age. Since then, the Earth has been heating up again, and there has been a corresponding build-up of emissions indicating a gradual increase in volcanic activity. We also know that 16,000 years ago, early man was still a hunter-gatherer. His impact on the Earth at that time would have been relatively small, so man did not cause global warming, which started 16,000 years ago. The volcanoes did. There are numerous excellent scientific works from the ice cores. In particular, Peter Ward in 2004, see the internet, clearly shows a period of most rapid warming between 15,000 and 8,000 years ago in Greenland ice cores, which is clearly contemporaneous with high rates of volcanism. Let's have a closer look at the temperature graph in recent history. The present is still on the far right. Notice that about 10,000 years ago we seem to reach a high point and have been generally trending sideways and slightly down ever since. At the top of the heating phase, we would expect the atmosphere to become so dense that the sun's rays can no longer get through, and we would start to dim and cool, as has happened 4 times in the last 400,000 years or so. Is this cooling already happening? We can speculate we are about to enter the next dimming and cooling phase, or according to some scientists, that we have already done so. Other scientists think the temperature rise in the last 100 years is significant and that we will go on heating up. Look closely at the zigzags along the temperature line. The main thing to remember is that even though the graph shows a general sideways trend, there are zigzags in the pattern of temperature change, leading to short-term rises in temperature followed by short-term falls, followed again by short-term rises, etc. Short-term could be as long as a couple of 100 years. People will go on arguing about what the temperature is doing right now. However, the real question is, has the temperature jumped out of the 10,000 years sideways trend line? But it might be more important to ask why there is such a dominating sideways trend in temperature. This has been going on for the last 10,000 years. This is an important aspect of all the graphs. Has this ever happened before in the history of the Earth? We don't have a lot of detail of the Earth's early history, but we do know in the cycles during the last 400,000 years, the temperature always seemed to reach a ceiling of plus 2 degrees centigrade to plus 3 degrees centigrade variation, after which it started to go down in a slow but fairly clear fashion. Have a look at the ice core graph again. Present time is on the left, and we're looking at the red line for temperature again. There's the plus 3 degrees centigrade ceiling in the previous heating cycle, and there is a plus 2 degrees ceiling in the one before. The one before that reached a plus 3 degrees ceiling, and the one before that only plus 2 degrees centigrade variation. But what about our heating cycle? It appears in the most recent temperature cycle we reached a plus 2 degrees centigrade variation about 10,000 years ago. The sideways trend then appears to be a new pattern. So we really need to ask ourselves, was the plus 2 degrees centigrade peak a natural ceiling, or would the temperature have gone higher up to, say, plus 3 degrees centigrade ceiling if man wasn't here? If we decide the sideways trend is a new pattern, then you have to ask, did anything change 10,000 years ago? As already discussed, we know that up until this time, man had been primarily a hunter-gatherer, and he remained as a hunter-gatherer for several thousands of years through the initial stages of our last warming period. Between 8,000 and 11,000 years ago, however, man first discovered he could cultivate plants for food. It is thought the beginning of the agricultural or the Neolithic revolution happened in about 5 or 6 different places around the Earth at a similar time, and then spread out from these centres. We could therefore speculate that in order to clear land for farming, man has been slashing and burning for the last 10,000 years, and this activity has been putting more and more soot, carbon black, into the atmosphere. You could call this the Soot Period, which started about 10,000 years ago and is still going on today. Soot in the atmosphere absorbs radiation coming in from the sun and also absorbs radiation coming up from the ground. The absorbed heat is transferred to the gas molecules, so the temperature rises, but it also absorbs the sunlight. So you have global dimming and global warming at the same time. In simple terms, we can say the presence of soot exerts a disturbing influence on the natural cycles of the atmosphere. This could be what has prevented the temperature going any higher than plus 2 degrees centigrade, and this could be what has produced the sideways trend in temperature. In other words, the volcanoes, through their natural emissions of gases, nanoparticles and heat flux, got us almost to the top of the normal warming phase, but man's activities may have interrupted the normal pattern. 10,000 years ago, most of the tropical and temperate zones of the planet were covered with trees of one sort or another. Look at it now. As well as continuing to slash and burn, man is also putting out enormous amounts of particles and gases which, just like the volcanoes, we would expect to have an impact on our climate. Here are two pictures taken from space of a recent volcanic eruption in Iceland. You can see the enormous amount of gases and nanoparticles ejecta emitted from the volcano. This image to the right shows how far this pollution has spread all the way across from Iceland to Europe. And here is an image of a human volcano or pollution over China. You could call the human volcano humongous. Keep in mind, the atmosphere provided partly by the volcanoes and the warmer conditions after the last ice age was highly favourable for the development of man and all the other species. Over the last 16,000 years, this entire natural system has provided us with an atmosphere and an environment that is comfortable for all of us to live in. However, we should not view the atmosphere and nature as being either balanced or unbalanced. This is not how it works. The atmosphere is always in a dynamic state and is never clear. We need the substances in the atmosphere for protection from the sun. The levels of these substances are always changing over time. The atmosphere, being extremely thin and fragile, will continue to operate at the mercy of any speed up or slow down in volcanic activity. It is also subject to all the other forces in space. These two natural forces are the primary causes of climate change. The atmosphere is also arguably influenced by the actions of man as a third factor. The natural cycles of volcanic activity have always contributed to climate change and will go on doing so. Cycles of increasing temperatures, like what has been happening over the last 16,000 years, followed by global dimming, cooling and freezing cycles, have happened many times before in the millions of years before man got here. This and previous cycles seem to be related to how much ejecta emissions, gases and nanoparticles, continue to be pumped into the air, and therefore how long the nanoparticles remain in suspension in the atmosphere. Man began to play an integral part in the atmosphere's integrity only 10,000 years ago, with the start of the Soot Period of slashing and burning for farming, which still continues today. About 300 years ago, man picked up the tempo and introduced the human volcano, humongous, in the age of industry. Together, the Soot Period and the human volcano seem to have contributed to an ever-increasing build-up in the atmosphere of a whole range of emissions and nanoparticles. If this follows what has happened previously, the rise in temperature will reach a tipping point, if it hasn't already done so, where the emissions will become so dense in the atmosphere the sun's rays will no longer be able to get through, and we'll enter a dimming period, eventually followed by cooling and freezing. Due to the increasing formation of ice, sea level will fall. Man will need to develop clean energy to keep warm as the temperature decreases if he wants to stay put in the temperate zones and not plunge himself into a premature freezing or migrate to warmer climes. Many scientists and governments are totally focused on CO2 and global warming at present. In fact, CO2 has hijacked the debate. But if you view man's contribution as a human volcano, then the picture becomes far more complex. Many people are sick of the naive concept that man invented climate change. Climate change is part of the natural cycles of the Earth system and everything beyond, and has been with us forever. Man is now a part of that system and may well have an influence on it, but he did not invent it. Politicians need to stop labelling people as believers or deniers and keep emotion out of it. We need to open up the scientific discussion. We need much more information about the behaviour of substances in the lower and upper atmosphere. Where are the scientists who understand the physics and the chemistry of gases and airborne nanoparticles? We should be hearing from them. Let's also hear from those volcanologists who study the volcanic cycles. And what about the gravity and astrophysicists, those who study all the different forces exerted on the Earth from the Sun and within our solar system and from further out in space? Our aim should be to provide the right environment for all such information to be discussed openly without fear of academic or financial reprisal. The ice cores show us the Earth's normal climate change cycle includes rapid rises in temperature followed by slow but clear falls in temperature over every 80,000 to 100,000 years. Within these major cycles there are also mini cycles of warming and dimming. If the Earth's history goes on repeating itself, then the normal major peak in temperature should be either plus 2 degrees centigrade or plus 3 degrees centigrade variation. At present we appear to be just under the plus 2 degrees centigrade level. Therefore we are either at or nearly at the top of a major heating cycle right now. Man may be influencing the shape of the normal temperature curve with what looks like a new sideways trend of zigzags in temperature at the top of the heating cycle. This sideways trend has been going on for 10,000 years, and it happens to coincide with when man started to slash and burn in what we've called the ongoing Soot Period. However, although the shape of the temperature curve may be trending more sideways than has happened in the past, it appears still to be going slightly down. This is following what has happened before, so we would expect the drift down to continue. It is therefore highly likely we will be well into a dimming period within the next 10,000 years or so. How does this fit with the current concern about global warming? As we said before, the real question is, has the temperature jumped out of the 10,000 year sideways and slightly down trend line? So far this doesn't appear to have happened according to the ice core data. However, any small increase in temperature over the short term, a few hundred years or so, can have a serious effect on our living conditions, so it is understandable many scientists are focused on this. It is absolutely critical to remember the Earth's history means it is extremely unlikely the temperature will go on increasing indefinitely. Long-term cooling is inevitable according to the ice cores. So let's not fiddle as the Earth dims by swapping CO2 credits in an emission trading fiasco. Cutting down on the whole range of emissions through practical direct action would be more to the point. The reduction of free-floating nanoparticles in the atmosphere would also have added health benefits for the entire population. In the meantime, the planting of trees is always good, but trees only address CO2. So a complicated financial system of swapping carbon credits will not solve climate change. Remember, trees cannot absorb methane. Trees really dislike sulfur dioxide, and trees are not able to capture nanoparticles. Here are some questions. Will a CO2 tax stop the output of sulfur dioxide, methane and all the other gases emitted by industrial man? Will a tax on CO2 stop the output of nanoparticles emitted by industrial man? And most important of all, how can we stop or at least slow down the continual slashing and burning of the planet? Well, there you go. Carbon dioxide, sulfur dioxide, methane and nanoparticles. Global warming, global dimming, global cooling and global freezing. Where will it all end? And do the volcanoes really give a damn? Thank you. Thank you for listening, and a special thanks to John Hillier and Anberto for making this production possible, and thanks to Wikipedia and the USGS for such fabulous images where the sources are duly acknowledged.